Okay, thank you very much, Claudia, for the very nice introduction. So, for those who don't know me, so I'm Edo, and what I do in my PhD is, as it says in the slide, so I create basically like fake universes using supercomputers, and and this is why they're digital. So it's my absolute pleasure to give this talk to the Astronomy Society, because as Claudia mentioned, I used to be part of the committee, and I'm really excited to actually give such a talk, and about this science that I'm doing for my PhD as well. So before we start, I want to give like a very warm welcome to everybody who's watching us on Zoom Live, but also for those of you who will be watching on YouTube when this video will be posted after today's talk. Okay, so without further ado, so I will be moving on to the first slide. Okay, so this talk will be about so the title of the talk is "The Universe in a Box." So the first thing that we think about when we receive like a parcel, for example, is that we want to open it because we're just curious to see what's inside. So let's just open this box to see what's inside this box, right? Because it says the universe, so like we'll see like what we're going to find in this universe. Okay, so and this is a little bit about what we're going to find. So we'll see that if we have a cutout of the contents of this universe, then we will see that the most of it is dark energy. Okay, so and this dark energy is something that we don't understand. Okay, so we know roughly how it works, but we don't understand. Dark matter as well, we don't understand, but we know it exists. Okay, so the only thing that we can actually observe is about 5% of the entire matter or energy that that is contained within the universe. Okay, but we see that our knowledge actually stretches only for a very tiny portion of this universe. So like most of it we know it exists. Okay, we know roughly how it works, but we actually don't know what we are dealing with on the fundamental level. Okay, so let's for example like focus on this dark energy. So this dark energy, we know it exists because it's responsible, we think, for the accelerated expansion of the universe. Okay, so and this is like a little bit of a meme that I was trying to make. So this was actually predicted by Einstein, and in this field equation, it basically it came up with this cosmological constant that mathematically is admissible from just from following the algebra. And it says basically said, okay, no, this can be true because the cosmological constant can make the universe unstable, can accelerate it, and so on. So, and then it actually turned out to be very relevant for modern cosmology, and he basically called this the biggest mistake of his life as well. Okay, so this is this is about dark energy. Okay, so we'll see what we're going to do about dark energy in those simulations. Okay, but let's set that aside for now, and then let's focus on dark matter as well. Dark matter was originally predicted, about 100 years ago, from independently from a number of scientists, okay, including Vera Rubin here, and this actually constitutes the matter that we can, hopefully try to detect one day. Okay, so through maybe you can, if you're a particle physicist, you can try to you can try and detect it like on a particle level. But if you're a cosmologist, you actually have to deal with it, every single day if you're doing research, okay? Because it actually constitutes 25% of the universe, okay? And this is about 5 to 6 times more than ordinary matter, so what we call baryons, okay? So that actually explains why you can't really understand atomic matter, as we see here in this pie chart, without finding a way how to model dark matter pretty well, okay? Because this is going to dominate your box, okay, your universe in the box, okay? So and finally, you know, just to have, you know, a really nice example of atomic matter. So what it actually is, so this constitutes the stars and the gas that we normally see in our observations. Okay, so we see stars in the universe, you know, different distances. We see stars in our galaxy, but also we see stars in different galaxies. And you know, and in this image, like, I particularly like it because not only we see stars, but we see galaxies, but also we see gas. Okay, so and this is ionized gas ejected from, you know, that is basically colliding with the relativistic jets from this black hole in the center of this galaxy. So the supermassive black hole at the center of this galaxy is ejecting relativistic jets, relativistic streams of electrons, okay, that then collide and slow down, you know, like, you know, when they collide with the surrounding gas, and they create these bubbles, okay? So, and we can detect it like through radiation, okay? So we have photons, and, you know, in this universe, and this is how we can get information from very far away, okay? But we also have neutrinos, and this is a very interesting and exciting emerging field, okay, which is not only relevant for particle physics, okay, or for solar physics, and we see, like, you know, the neutrino oscillations were first discovered, but also they are very relevant for simulations. And this is something really, really new that, you know, if you, you know, if I would have given this talk maybe a year ago, I wouldn't have probably included the neutrinos in our picture, okay? So, and I wanted to finish off by with this slide by talking about black holes, because they, yes, they constitute basically, you know, like a very insignificant amount of mass, okay, but they're very, very important for the universe, because the black holes alone, they, you know, they contain pretty much all the entropy that there is in the universe, okay? So all this tiny fraction of mass, but they actually, you know, but those black holes alone, they contain actually, you know, about 99.99% of the entropy of the entire universe. And this is something that was first, you know, predicted by Stephen Hawking, and, you know, and led to this, you know, incredible amount of research, you know, with the information theory with black holes and so on. Well, yes, we do include also black holes, but we model them in a very particular fashion, and we're going to see, you know, how this is going to play out. Let's move on, and let's actually see, you know, what we can do with those, you know, with those things here. Okay, so we have different components, as we saw in this pie chart, and, you know, and we can see if those are independent, or we want to know if those can interact with, you know, with one another, and, you know, how those interact. Okay, so we talked about, first of all, we talked about dark energy. Okay, and dark energy is the you know, is what basically causes the acceleration of the universe. And turns out that, you know, that it actually plays an important part, but, you know, for as far as we know, it doesn't really contribute to the formation of galaxies themselves. Okay, it just contributes to the accelerated expansion of the universe. Okay, so in our simulation, since we want to simulate the formation of galaxies, and since we know that dark energy doesn't play, you know, a very important role for the formation of the galaxies themselves, then we can basically like decouple that, like, from the rest of the processes that we're interested in. Okay, so in this, you know, the way I want to show this scenario, and we can actually treat this analytically. So once we know omega lambda, so how much dark energy there is in the universe, okay, and we can measure it like somehow. So once we know how much dark energy there is in the universe, then we can basically, you know, decouple that from the rest of our contents of the universe. We can basically, you know, and we can basically treat them literally like almost with pen and paper. Okay, so we're not going to have dark energy in our universe, because that's relatively easy compared to the rest. Okay, and we want to use, you know, very big machines to do the hard stuff for us. So something that we can't do with pen and paper. Okay, so we want to optimize our efforts. So let's focus on the other branch, okay, in this broad classification. So, and let's focus, let's start with the, with the center tile. Okay, so dark matter. So we saw that the dark matter, is very important for the evolution of structures because, it constitutes, a portion, fraction of the universe, which is much bigger than, the matter that we can observe. Okay, so, and well, we don't know much about dark matter either. So, but the only thing we know, and the only thing that we are pretty sure about, is that it interacts gravitationally. Okay, so it doesn't interact, with in any other form as far as we know now, but it does interact gravitationally. Okay, and so in our simulation, what we want to, if we want to model dark matter, then we'll want to model it with gravity. Okay, and nothing else. Okay, so dark matter, it just interacts with gravity, and it only has this type of interaction with other components. For example, if you have stars, then dark matter, so the only way that dark matter can interact with stars is through gravity. Okay, and the only way dark matter can interact with black holes and the gas as well is through gravity and nothing else. Okay, so this is going to be very important. So only gravity for dark matter. So let's take a look instead at the gas. Okay, so the gas is a little messier. Okay, because it not only does it interact with gravity, but it also it's a compressible gas. Okay, so you imagine it's like air, for example. You can compress it, you can increase its temperature, and you can shock it, for example. You can even have sound waves inside the gas. Okay, so in principle, you could have even sound waves in in the gas around galaxies, for example. Okay, so, and this is something quite interesting that we won't get into the details of, but this is just to give you a broad idea of what are the players involved here. Okay, so you have gravity for the gas. Okay, the gas has a mass, so it interacts gravitationally, but it also has some pressure effects, correlated with it. Okay, that we need to take into account if you want to model galaxies, which are, also composed by gas as well as dark matter. Okay, so, and then this gas can, as we said, you can associate a temperature to the gas, and this gas can radiate away, like energy in the form of photons. Okay, can radiate thermally or can radiate through another process. So it can cool down. So because if the energy is dispersed, so if the energy escapes from the hot gas, then the gas cools down because it has less energy. But if the gas cools down, then it can't counteract gravity anymore, and it eventually collapses and forms stars. Okay, so you see the gas is also correlated with star formation, so with the way the stars form. Okay, so, and stars can eventually, at some point in their lifetime, can also collapse and form black holes. Okay, so, and those are going to be slightly less massive than the black holes that we find in the center of galaxies, but but this is just to show that gas stars and black holes have much more complex correlation than dark matter. Okay, so we're actually going to see how we can get everything to work in our simulations. So we have dark matter on one side, okay, which only has gravity, and then we have the rest of the physics that has gas, gravity, there's gas with gravity, but also stars and black holes with other different processes as well. For the neutrinos as well, there is, as I said, this is a very interesting and important, component that is being introduced in current simulations. Okay, and that changes basically, that changes, quantities, observable quantities to maybe like from 1 to 3% level. Okay, so you want the neutrinos if you really want to get very accurate simulations. So if you want to do, if you want to have a rough estimate of how the universe can be simulated, then you can get away with gas, dark matter, black holes, and stars. But if you really want to get the 1 to 3% accuracy, then you really need to include the neutrinos as well. Okay, so, and this is something which is really exciting, and it's gonna is going to lead the path to, our, to some of our projects, which really target, precision cosmology through simulations as well. Let's move on and let's actually see why should we actually bother simulating the universe? Since the universe is a really large environment, then it's basically possible that we can find like all the scenarios that we're looking for in this universe. If it's so vast, then statistically we can find pretty much all possible configurations of galaxies in this universe, right? So why should we bother actually simulating one in a box or in a supercomputer? Okay, so there are many reasons. Okay, what I tried to do here is to show to group them in different categories and to actually see like what to actually show some of them that I think that they're quite relevant. Okay, there are more technical ones, but those are the ones that are those are the pillars of what we actually want to why we want to simulate. So we can start with a statistic statement, which basically says that we only have one universe we can observe. Okay, so if you want to observe a different universe, okay, then you're going to move out from the current universe and go somewhere else, like hypothetically. So this is not really like a really good way of doing it. Okay, so and a better way of doing it is to instead like simulate a universe so that you can make a copy, okay, of a universe, but changing maybe like some parameters a little bit, and that's gonna do the trick essentially. Okay, so on statistical grounds, then it's useful to simulate universes, okay, because then you can compare your simulated universes with your actual universe, with your real universe, and you can have more statistics to play with. Okay, and statistics is really important for science, so this is why this is also a very important reason why we want to do this, but also a philosophical reason, because if you're just observing the universe, then this is basically like passive approach. We can't really change. We can't really go there like in to a very far away galaxy and change how things work. We can't we can't basically decide whether or not supernova a supernova is going to go off or not in that galaxy. So for two reasons. So the first reason why we don't really have control on supernova explosion. The second reason why is because when we actually see that supernova going off, that supernova actually went off, millions of years ago. Okay, so we can't really travel back in time. So so another cool aspect of computer simulation is that we can actually switch to a new paradigm, okay, if you want to think about it this way, and we can take an active approach of building the universe like from scratch, if you want. Okay, so if you want, so if you don't want supernovas because for some particular reason you don't like supernovas, then you just tell your computer not to include supernovas, and and you're going to have a copy of the universe where you have no supernovas, and it might be interesting for some reason to know what it looks like. Okay, or if you want a universe without dark matter, say, okay, so there are actually like some people who are trying to explain the rotation of galaxies or the velocity dispersion measures without dark matter, and they actually want to know if a universe can even possibly work without dark matter. So what do? You can't really take the dark matter out of our universe, or but you can take dark matter out of the simulations, and you can see how galaxies change, will change their shape, or it will change their sizes, or so on, how the properties of galaxies change if you change the contents of the universe, if you change the physics. Okay, so you can also change the physics in your simulation. This is why it's so cool, because you have complete control over it. You have an active role. But you also have a better way of exploring this physical complexity. So we saw in the previous slide that a lot of these processes, they are very intricate, and they don't really, they don't have an analytic solution, something that you can solve with pen and paper, okay, because it's very, very diverse and complex, okay, as an environment. And this is why we use simulations, because because structures can start growing non-linearly. So when the matter starts collapsing, first of all, then you can still do the calculations with pen and paper, okay? But then after like, you know, a specific point, you know, where, you know, the matter starts collapsing even more, then the collapse becomes non-linear. And then it's really hard to keep track of all the terms like on the pen and paper. And this is why you use computers to do that for you. Okay, so but you also have another scenario, which is multiphysics. Okay, so you have all these different types of physics involved, including gravity is one of them, is the leading one. But you also have the cooling of the gas. Okay, so gas cools, you know, increases or decreases its temperature. Okay, so but you also have star formation. You also have other processes. For example, you know, if you want to model black holes ejecta, so you want to model, you know, the jets emitted from the black holes, that's going to be some extra complication to your, you know, to your picture. And this is also why, you know, computers are very good at dealing with this. Humans are, you know, probably, you know, in a way less good at dealing with such complexity, but only because we can't really, you know, parallelize as much as computers can. Okay. So, and also, you know, we want to, you know, we want to minimize our effort, you know, to want to use computers to basically do that. But you also have some other feature that the universe has, and we want to replicate in our simulation, which is this huge range of scales. Okay, and this is what I wanted to show you in this picture here on the top right. Okay, so what this picture is an image of a simulation of a galaxy cluster. Okay, so a galaxy cluster is an assembly of many galaxies. Okay, so it's basically a group of many galaxies. Okay, and you do see like some galaxies, for example, like in these cutouts, in this like insets, for example, here and here. So if you zoom in, then you do see galaxies. Okay, but if you zoom out, you still see like this structure. Okay, this very big structure of the galaxy cluster, and you want to model the big structure of the galaxy cluster as well as the individual galaxies. But this is really complicated because you need to model the physics. You need to get the physics right at different scales. Okay, so you want to get galaxy clusters right, but you also want to get galaxies right. Okay, so and the physics that works on galaxy clusters might not work on galaxies individually. Okay, so you need to you have this huge range of scales, like from you know, pretty much a big chunk of the observable universe, so of the order of gigaparsecs. Okay, so this is a I can't do calculation on top of my head, but this is like 3 billion light years, more or less. Okay, and you basically want to resolve, you want to be able to zoom in into that picture and resolve structures which are, you know, maybe like a few parsecs across if you want to resolve the spiral structures of galaxies. Okay, and this poses a really challenging, aspect of simulations, which is, you know, the huge range of scales that we need to deal with, the huge resolution that we need to be able to do this. Okay, again, you know, we have resolution issues, and you know, what we can do about it, we use supercomputers to actually do it. But also the time evolution. So gravitational collapse. So structures in the universe collapse of the order, you know, like with a time scale of the age of the universe, basically. Okay, so within the age of the universe, then a galaxy cluster will actually form and collapse. Okay, but then within that you have all much shorter fluctuations. Okay, much shorter processes that take, for example, a few years. For example, if you want to model the variability of a black hole, okay, how much energy does the black hole eject, you know, the surrounding gas, that changes in a matter of years. So you want not only spatial resolution, but you also want time resolution, because all these things are evolving with time, and you want to also capture that in your simulation, in your universe in a box. Okay, so these are like some of the challenges that that pushed like many researchers and scientists to develop these cosmological simulations. Okay. So, but these are actually, so there are challenges, but also there are good sides. Okay. So, and one of the good sides, or at least, one I particularly like, is that, you can basically add components one by one, and you can turn on physics one by one in your universe, so that you can basically see exactly how adding one single component at a time in your universe, how they're actually changing your evolution of galaxies, for example. So you start with dark matter if you want, okay? And you see in the universe has some properties, but then you say, okay, now I want to see what the effect of gas is, okay? So you add your gas, and you can see the difference between your universe without gas and your universe with gas. And you can actually see, what you can actually weight like those, those two universes and see, what the properties are like. Okay, so and you can do this also with other types of components, for example, stars, and also other physical processes. If you don't want supernovas, again, for some reason, then you can compare a universe with supernovas and another universe without supernovas, and you can see how those two things compare. Okay, so they're really like Lego bricks, where you actually add things one at a time, but and I think there is a much higher chance of all this to make sense if you do it this way, when you go from just the individual Lego bricks and you put them together into some more complex structure. Okay, so there is a high chance that in my opinion, that it will actually make sense once you actually have all these pieces together. Okay, so I think it's more friendly used to learn, more user-friendly to learn this way, essentially. Okay, so let's start with dark matter. So here in this movie, we have if we are flying through one of those simulations that only contain dark matter. Okay, so and one of those so I think the most striking feature that we see in those simulations is that all the halos of dark matter, all the objects and all the dark matter galaxies, they look almost the same, right? So, and this is something really interesting, because they they are supposed to look almost the same, because they only interact gravitationally, and they don't have pressure effects. Okay, so this is basically this is a very nice movie of the Millennium 2 run. Okay, so this is a dark matter simulation, dark matter only simulation that was run a number of years ago, by the people in Munich and MPA. Okay, so and all there is to it. So all it took to basically create this simulation is, of course, a relatively big supercomputer, but also just the gravitational force. This is just gravity. This is a universe where it's fully dominated by gravity. Okay, it's not just this 25% dominated by gravity, but it's 100% dominated by gravity, and this is what's shown here. So, but this is also very instructive, because your simulations will be dominated by gravity, because gravity is much is 25% of the overall energy density of the universe. Okay, so energy content of the universe. So it's much so it's 5 to 6 times more than the atomic matter. Okay, so it's really useful to learn how gravity and dark matter works at many different scales. And it actually shapes the skeleton of the universe. Okay, so and it does create also these very nice structures, as you can see here, and those are often referred to as the cosmic web. Okay, so and we'll see that in the next slide as well. So and so just to summarize, so we don't know what dark matter is made of on a subatomic level, but apparently it's actually the easiest to simulate, because all there is to it is gravity. Okay, and we know how gravity works because we have many theories of gravity. Okay, so we have Newton's gravity, but also we have Einstein's gravity. So, and now some of you might ask, so which one do we want to use? Do we want to use Newton or do we want to use Einstein for modeling our gravity in our simulations? Well, people have tried both, of course, because this is a really good and fundamental question that we want to address. And it turns out that the densities that are involved in our simulations, okay, in galaxy classes, they are very, very low density. And when you have a low density in the universe, then Newton's law is okay to use, okay? So the general theory of relativity is only very important when you have very high dense regions of space-time. For example, like next to a black hole, then Newton's laws break down, and you really need to use the Einstein's field equations to describe the motion of of a particle around the black hole and so on. Okay, so but we can't get that close to the black hole still because we don't have the good enough resolution, and as long as we can model the black hole really, really well with that with an incredible amount of resolution, then we don't need to worry about general relativistic effects. And this is why we just use Newton's law to describe our gravity in our simulation, which is good news, because people have found out that just switching all the simulations to general relativity, it actually makes very little difference to the overall results, but it takes a huge amount of time to actually run compared to just Newtonian gravity. So general relativity is good if you really have a good reason to do it, to actually use general relativity, but it's more expensive computationally. Okay, so this is why we often opt for Newton's laws. Okay, so let's see what this how we can model this kind of gravity with Newton's laws. So if you have two galaxies, okay, then you can basically build up your n-body problem where n is equal to 2, so you have only two objects to worry about. You just as most people like in physics know, this is quite this is not a particularly complicated problem. You just need to do one calculation. You just need to write out one equation, okay, and then you have the force. Then you have you can compute the gravity between those two objects. So only one calculation for those two objects. Let's actually move to three objects, because there are many galaxies in the universe. So like we want to populate our box with more and more galaxies, and let's make it like three objects, for example. Okay, so when we have three objects, then somebody called Poincaré actually demonstrated that you can't really write, you can't really solve equations for three-body three-body systems analytically. Okay, so just moving like from two objects to three objects, it gets more complicated to solve like with pen and paper. Okay, so and of course you have in this particular case you have like three forces to compute. Okay, so you have the force between this galaxy and this one and this one, and the last two. Okay, so you have three forces, three calculations for three objects. Okay, so if you populate your box with more and more galaxies, what you'll find is that if you increase the number to 4, then you have 6 calculations. And what if you want to calculate hypothetically all the galaxies that are in the universe? So the current estimate is that there are about 2 trillion galaxies in the universe. And if you actually use this method for simulating your gravity, then with each particle is one galaxy, of course, then you will need to do 10 to the 24 calculations. So a trillions calculations. Okay, which is a lot. Okay, so and I mean, like it's actually like it poses a really I wouldn't say insurmountable challenge, but it's very, very complicated to actually do. Okay, and what if you want to model spiral arms for galaxies, for example, or the internal structures of galaxies? What if you want to model individual stars in the galaxy. Then the stars in the universe, then there are basically like 10 to the 25, and which will basically mean that you will need to do like 5 times 10 to the 49 calculations. Okay, so well, you can basically, you can hypothetically, tell me wrong, if I made a mistake there, but if you want to build a supercomputer capable of doing these many calculations, you will probably run out of all the silicon in the universe, okay, just to build that one supercomputer. So you're physically limited by the amount of silicon in the universe to build a supercomputer capable of doing that kind of calculations. So this is just to say that we need a better way to do our gravity, okay? So, and this is often called an n-squared algorithm, because if you multiply like this, if you make this polynomial explicit, then this proportion to n squared, and basically your number of calculations just grows extremely rapidly, when you have more and more bodies in your system. We need a better way to actually do this, and we agree on this, hopefully. So the other way of doing it is that, so imagine you are on this particle here and you are an observer, then, and you're feeling the gravitational pull from particles or galaxies which are far away, let's say up here, then it won't really matter if you can, so you won't really feel the difference if you just model the gravitational attraction to each single individual particle, and so it won't matter to you, and it will be just exactly the same, pretty much to a very good approximation to just one bigger particle or galaxy that sits, more or less in the barycenter of these smaller galaxies here, but will have basically the same effects on your position here. Okay, so it's basically about grouping galaxies which are very, very far away in your universe, and just combine the gravitational attraction for all of those, and just without modeling each individual galaxy by itself. Okay, and when you're nearby, then you need to model each individual galaxy. But when you're far away, you can be more rough in your approximation. Okay, so you can be a little bit more forgiving and just group the particles together. Okay, so if you do this, then you actually end up with a much nicer scalability relation, so that your algorithm, so the number of calculations that you need to do when you increase the number of particles, now doesn't go with n squared, but now just goes with n times the logarithm of n, which is, like in mathematical and computational terms, is a much nicer relation. So that means that if you just grow your number of particles, then you don't have many more calculations that you need to do in order to solve your problem. Okay, and this is really a really good way forward for modeling dark matter. Okay, and this is called the tree method. Okay, so we won't get into the details, but this is basically mostly how it works. Okay, so what are, like how many galaxies or how many particles? So remember, like in this particular case, you can consider that each particle is a galaxy. So how many of these galaxies are in our current simulations? The ones that we normally run. Okay, so if you have everyday simulations, okay, so those are the ones that, for example, like I'm running, I think about 30 at the moment. So, and those are considered pretty much everyday simulations. Those contain from 1 to 10 billion particles. Okay, so from 1 to 10 like billion galaxies if you want. Okay, so and this is a 10 billion body problem. Okay, which is extremely complicated if you want to do it, with the old method, but it becomes manageable if you want to use it. If you want to use the tree method. Okay, so in particular, I'm running those on just one single computer. If you want, you don't even need like a supercomputer if you want to run like 10 billion particles. You just need a lot of memory, okay, and a good CPUs. I think I'm using like 28 cores, so like it's a bit bigger than the average computer, but it's doable without too much effort. So if you want to move to large simulations, then you have 10 times more particles, okay, and those are simulations that take a good fraction of your supercomputer. But if you want to use two flagship simulations, then you have of order of the trillion particles. Okay, so you really can stretch your simulation to simulating pretty much the entire observable universe. Okay, so just very quickly, I wanted to show you like some examples of everyday simulations, like this, for example, one that I was working on. Okay, one of the pseudo simulations that was running. So this with dark matter only. Okay, so this is how the structure looked like. Okay, so you see the filaments of the cosmic web here going on the sides, but this is basically one big galaxy cluster, and you see like many satellites, and those are going to become galaxies when we add also gas and stars in them. Right now it's just dark matter. So, but if you zoom out, okay, so from this simulation, you want to see what a large simulation looks like, then this more or less what it looks like, and this is the Millennium 2 that I showed before. And you can see the cosmic web much better here because you have much larger volume. So you're not concentrating in just one single halo. So more or less you can assume that this one is more or less equivalent to this region here. Okay. So now you can simulate a much larger volume. Okay, but it's not quite as big as the observable universe. Okay, so which brings me to showing you what a flagship simulation looks like. So stay tuned for this one because I hope it's gonna look exciting. So there we go. So this is an example of a flagship simulation with about 4 trillion particles. Okay, so this is again, this is just dark matter, and this is supposed to simulate pretty much the entire observable universe. Okay, and this was done like 4 years ago by the Euclid Consortium, and that took an entire supercomputer. By entire supercomputer, I mean like the supercomputer just shuts off to everybody else doing calculation there, and is just reserved for that one calculation, for that one big simulation to run. Okay, so this is a big deal. Okay, to actually run on a very large supercomputer, because it means that you reserve your supercomputer just for you for several months of calculations to actually produce something that looks like this. Okay, so and you can still see the cosmic web, but now your galaxy clusters, they're very tiny, so you can't see like in this configuration here. So you really need to zoom in to actually see one of those. Okay, so I think you might be wondering, okay, so how can we actually do this with supercomputers? So what is the we don't have on laptops, then we can instead like do on supercomputers? Well, you could in principle run a small calculation on your laptop. You can run a small simulation on your laptop, but what really supercomputers are good at is doing calculations together. Okay, so you have in supercomputers you have many units of computing, which actually act together, and you can really parallelize. You can distribute your calculation across like all these nodes. Okay, and this is what generates this step up from just normal laptops or just normal workstations. And this is the supercomputers that this one of them, this the other one here in the back. So these are the ones that we're actually using, my group and my collaborators. So this is these are some supercomputers at Durham University. There are actually a national facility, so it's not just us using them. There are also like people from from like epidemiology as well, like for modeling, a whole bunch of different things. So these are national facility machines as well. Okay, so we're going to come back to supercomputers at the very end, which is not going to be like which is not too far. But first, I want to talk to you about what happened to the baryons. So right now we just talked about dark matter, and but we want to actually see some pretty galaxies, and to actually model how the gas affects the evolution of galaxies as well. So I wanted to basically play this this nice video. This also a zoom in into one of those simulations. And what you basically see here, I think if the rendering is not too bad, is that you see a galaxy here in the center, and you see like all these filaments of gas collapsing onto the galaxy under the effect of gravity. Okay, and basically you see that when you zoom out, then you actually see the the entire volume of this simulation. And you see that this galaxy actually starts rotating to some extent, and this is also what generates the angular momentum in the universe. So those structures collapsing onto that galaxy and start spiraling around. So this is how angular momentum is generated in the universe. And this in this nice movie, I think shows that very, very well. So this is done by one of our colleagues, Roper Sussex as well. Okay, so what you can see here is that you can immediately say that they are baryons are much messier than dark matter. Okay, so it's actually easier to observe them, but it's actually much harder to model them in our simulations. So, and this goes back to what we were saying before. So due to their intrinsic physical complexity, so the structures, as I said, they grow non-linearly. So when you really zoom in into that galaxy, then the environment is very complex. So, but you have also different types of physics actually playing into this, into this image here. You have, you have gas cooling, and you also have like some supernova going off and so on. And you really need to get, write the simulation from the very last scales of the entire box down to the very small scales of your galaxy. And this is also another tricky thing to do. So what is the grand challenge of simulating baryons? So it's basically to reproduce the observations that we know that we know very well, okay, to actually make new ones, to make predictions, okay. So, and this is really like our job as theoretical and computational astrophysicists, to actually reproduce what we know they are, they are the correct the correct way of reproducing observations. But our job is to also make new predictions and point observers to the right direction, okay, for making some discoveries. So discoveries, of course, not always happen this way, but this is our job to basically trying to predict some observations that can possibly be done with in the real universe, and point the observers to the right direction. All right, so I want to just finish by giving you one very nice example of this simulation with all the physics in it. So like in this image, you see like the gas, you see like the temperature, you see dark matter, you see like some pressure shocks, and you see also some metals here. Okay, so, and this is just to give you an example of one of the simulations that are in the process of making, and they really are hoping to revolutionize. I'm not saying revolutionize, but to basically create a really to provide a really nice data set with which to actually observe, to predict new effects that we can observe in the universe. So this is the Eagle XL project. So it's also my pleasure to introduce you to this project. So you will not hear about it quite yet in all the talks, because this is still in the making. But I can already anticipate it that that it's going to make quite a bit of noise, at least in the community. But also it's going to have like some nice press releases and so on. So this is a team of international interdisciplinary team of about 50 scientists, including myself, and also my team at JBCA as well. So it's going to use a new supercomputer. So it's called Cosma 8. and that's going to be hosted. It's also a national facility. It's going to be hosted at Durham University, and that's going to consume about I think like 250 terabytes of RAM memory. So it's going to be huge data set produced, and we're basically waiting for big data for many astrophysics applications. Okay, so what is cool about this is that this is our our most recent simulation that we actually have. It's called the Eagle simulations, and this is going to be not just with better physics, but it's also going to be a larger volume. And this gives us many more galaxies to get that information from. Okay, so let's skip that for now. Maybe if you have a specific question, then we can get into this calibration. So like how we can tune this physics, to get the right parameters for our observables. But but let's keep that for now. And I wanted to show you that little movie. So this is also something that I was just making for press release purposes, also, but for the Eagle Excel project. And so this is like 3D visualization of one of those clusters. And this is like a rendering with some shocks, some like shock waves that are generated gravitationally. But I just wanted to finish this talk very, very quickly with, with taking a look at the future of supercomputer simulations. Okay, so right now we're using supercomputers that, that can do, they can basically do like, 10 to the 15, about 10 to the 15 calculations per second. And those are called flops, floating point operations per second. So the dream of a computational astrophysicist is to get to exascale. So exascale is the next frontier for supercomputing. Okay, so and this poses different challenges. Okay, not just for our code called Swift, but also other codes. Is that it's a hardware challenge because you need to have a hybrid, so a mix of CPUs and GPUs. Okay, but you also on that scale also matters how you actually arrange your computers. Okay, so the topology matters. Okay, so but you also need to be capable of producing software. Okay, some code that is that is capable of that number of cores. Okay, and in some cases you might actually need to build some very low level libraries from scratch. This is something there's something in the group at Durham University is actually actively really working on. It's very interesting to actually see what's going to come out of this. So, and this picture is actually a supercomputer which was inaugurated not very long ago. It's called Fugaku. It's in Japan, and it's capable of producing 10 petaflops per second. Okay, so and that actually well, it might seem like very, very far to the exascale, because if you want 1 exaflop, then you need 100 times this. Okay, to be optimistic and look problem in a log scale, a really huge threshold, a really huge barrier to actually break through. But it's going to be as the word says, it's going to be a breakthrough not only in the field of cosmological simulations, where we're going to have huge resolution and very many different scales, better physics and so on, but also for a lot of other applications, particle physics, also hydrodynamic simulations for engineering and many others. All right, so with this slide, I wanted to introduce our friendly team at JBCA. So at the moment there are 4 people working actively on hydrodynamics and full physics simulations, and of course but we know, and everybody knows, that there are many other very talented and very keen young scientists out there. So if you develop an interest in cosmological simulations, please do get in touch, and we look forward to broaden our team, okay, and to welcome new members. All right, so I will conclude with this. Just a reminder that if you're watching YouTube, please give a like to the Astronomy Society, which I want to thank again for hosting me, for allowing me to join today. And don't forget also to subscribe for a very exciting talks in the future, especially the one next week from Jocelyn Bell. So thank you very much. That's all for me. And Claudia, the stage is yours.
Yeah, thank you so much, Edo. That was really interesting.
Questions, please also.
Yes, if people have questions, they can put them in the chat. They can unmute themselves. It's okay. Oh, do we have a raised hand from Takagi?
Hello, can you hear me?
Yeah, hi.
Hello. Long time no see, I guess.
Yeah, definitely.
Yeah. So I just wanted to ask a quick question, actually two. So what's the main sort of difference in sort of regarding implementation of neutrinos and baryons? And also, I just wanted to ask how you sort of fix the sort of initial position of these sort of particles or galaxies when you sort of do these simulations. Do you actually try different configurations as well for the same sort of simulation?
Oh, that's so there are two like excellent questions. So thanks for actually asking. So when you have neutrinos, basically you don't, and like it actually depends, on if you assume that they're massive neutrinos or not. Okay, so this simulation, so the reason why we want to include neutrinos is not just because we want to be picky about the 1-3% accuracy level, okay, but also because we want to because we know that if you change the mass of the neutrinos, then it actually changes how some of these properties of the galaxies. Okay, so using cosmological probes is also a very key method for investigating, for calculating or trying to measure the mass of the neutrinos. Okay, and there are surveys like DESI which really aim at doing this from cosmological, from actual data from the real universe. But that is going to happen a few years in the future. But before that happens, by the time that happens, we want to be ready. We want to really understand what's going on in our fake universes. Okay, so how these are implemented. So what it actually changes is it could change, for example, like the shape of galaxies a bit. How the size of galaxies as well. But what it really changes is the overall power spectrum, like matter power spectrum of the entire universe. So like these are global properties, not just individual galaxies. Okay, so on an individual galaxy level, then you might change like just a little bit, but so you really see the effect if you just average from you just average out like many different galaxies, and you see the overall effect. Okay, I hope that that answers. So for the second question, so that's also very interesting. So these simulations are a bit like if you've done math courses, then it's like solving like an ordinary differential equation. So you need boundary conditions and you need initial conditions. So our boundary conditions are kind of easier because we want to simulate an infinite universe. So what you can actually do is that you set your boundary conditions as periodic, which means that your simulations become like a little bit like the snake game. Okay, so if a galaxy crosses one boundary, it comes out from the other boundary. Okay, so in this, these are the boundary conditions. Your initial conditions are trickier because you can actually solve this analytically. You can actually solve the evolution of structures analytically up to some point in the evolution of the universe. At that point, which is about redshift 127, then you stop, And then that's the point where things start going non-linear. Okay, and that's where you actually take your initial conditions and then you evolve them through a different type of process. Okay, so your initial conditions are basically pre-processed, if you want, in such a way they will form galaxies. Okay, so and that's done by a separate software, and you generate your initial conditions and you evolve those initial conditions through a different type of process to generate galaxies and so on. Okay, so those initial conditions are not random. Okay, so you actually start from a random field, but your random field is also displaced just by the tiny amount that's necessary to form structures. This, of course, this is backed up by maths and so on.
Okay, I see. Yeah, I really need to go now. So thank you so much for the talk.
Okay, no worries. Glad you liked it.
We have a couple more raised hands and also some questions in the chat. So Peter, if you want to unmute.
Yeah, hi. Really good talk. Thanks for that. I missed a little bit at the beginning, so apologies if you already covered this. But I just wanted to go back to the point where you were talking about the baryonic structure of the universe. And you mentioned something about the angular momentum of the universe. And that it kind of blows my mind a little bit. And I was just wondering if you might be able to sort of describe what you mean by that. Yeah.
So yeah, I actually went through that like a little bit fast. I do realize this. So basically, how you generate. So if you ask yourself the question, so why do galaxies rotate? Okay, so where do they actually get the angular momentum from? Because the universe as a whole, right? So if you take the whole universe, then you can't have an angular momentum, okay? Because it's otherwise it becomes a problem for cosmology itself. If the entire universe has a residual angular momentum. So overall, your angular momentum of the entire universe is 0, but somehow on smaller scales of galaxies, somehow it appears.
Right. Okay.
So and that's quite puzzling. At least it is to me when I was thinking about these things. So where the angular momentum comes from is when you have structures of like pieces of dark matter or baryons collapsing gravitationally onto one object. Okay, so they might not collapse straight head on. Okay, so if they have a set parameter, then they won't actually collapse directly head on onto the object, but they will just be captured by the gravitational of the actual object orbiting. Okay, so that set, when the structures collapse, that's what generates the angular momentum in galaxies. And that's basically transferred back onto like solar systems and so on. So it's it's that game that generates angular momentum.
Okay. Yeah, that makes a lot more sense. Yeah, thank you.
That is relatively clear. Interested in that, then there's an actual paper coming up, so stay tuned.
Okay, I'll keep an eye out.
On the mathematical side, anyway.
Cheers.
Nice.
We have another question and a raised hand by Tim.
Yeah, so this is more on the computing side, but when you say you parallelize the process and you extend it even to the supercomputers and so on, is it just simply assigning certain or more cores to certain parts of the universe and parallelizing it that way, or is there something more, something different that you're doing there?
Well, it's it's a very interesting and very open question in our field. So basically, the first thing we do when we simulate this is that we divide this cube, let's say, okay, this box in equal cells. Okay, so we basically set a grid and we make it look like something like a Rubik's cube. Okay, so and the easiest thing to do is to say, okay, so the first little cube on the bottom, then you assign it to node 1, and then the one after that you assign it to node 2, and so on. Okay, so that is the one way to do this. Okay, but then you realize that those two little cubes that live on two different nodes. Okay, so they might have some particles, some galaxies that hop from one cube to the other and so on. Okay, because those things have a velocity and they're evolving with time. Okay, so your two nodes need to talk to each other to basically say that the one galaxy is hopped to another cube and so on. Okay, so you need communications also between the nodes. It's not just that you set your grid at the start and then that's it for the rest of the simulation. So you need to update this every time, and so you need to create communications like all across your supercomputing network. Okay, so and this is quite interesting because there are different ways of doing it, and some work, some other don't. Okay, but so what you end up with is essentially is basically like different cubes in your volume. You assign each one of those to a different node in your cluster, and at that point, it's just a matter of like communicating, from one node to all the others, where the particles are and what they are doing and stuff like that.
Yeah, that makes sense. Thanks.
Right, we have a couple of questions in the chat as well. So Danizon asks, why grids/cubes and not spheres for the total volume of some of the simulations? And how does a snake transport of galaxies at the boundaries not cause problems?
Okay, so there are very interesting questions actually. So in principle, there is no constraint about spheres or cubes, like whether you choose one or the other. So in fact, like some of the simulations, like that one that you see here, that was actually a simulation drawn from sphere. Okay, so but that one is a cube. So the cube is easier because you have well-defined sides. Okay, so if you have one particle going, crossing the boundary, then it's gonna basically come out from the other side. Okay, so that's just easier to code up, like in actual code, so that just for convenience. Okay, so the reason why you would want to choose a sphere is that if you're not really interested in this boundary, okay, you just want to simulate. You want to take maybe like just a very tiny portion of this very large box. Let's take, for example, this object here in the middle, and you want to resimulate it with higher resolution. Okay, you want to really see what's happening in there. So, and this is a technique called zoom simulation, which uses the default, a spherical region, okay, around it. And this is, an example of that. So this is a zoom resolution taken out of a box like this one, for example. Okay, so you can have both spheres and cubes. You have cubes for convenience, and you have spheres when you really need it, because it's slightly more complicated to actually code up. And what was the other question about baryonic physics?
Yes, if the snake transport at the boundaries causes any problems. Okay, so
yes. So the fact that you have boundaries and you don't have an actually infinite universe, they do cause some problems. Okay. So if you choose the periodic boundary, so if you just make the one galaxy go from one end to the other and come out from the other wall, so that's something to basically fake an infinite universe. Okay, so it's not actually a truly infinite universe. So it's topologically infinite because you never reach a hard wall. Okay, so but it's not actually a true infinite universe, and this creates problems. For example, it's going to have some effects. So if you want to study these filaments, as you see here in this picture, then you see that these ones, for example, if you take these ones and that one here, these very, very long ones, they are pretty much perpendicular and parallel to the sides of the box. So if you're studying like filaments which are comparable to the size of the box, those will be affected by your finite size of the box. Okay, so those will be affected. But if you take a very, very little galaxy here, that will basically have no effect. That will take no effect from the fact that your box is a finite size and you're using periodic boundaries. Okay, so it does affect to some extent, but only if you're considering structures which are, comparable with the size of the box. If you're just interested in a galaxy inside it, then it doesn't really matter.
We have one more question in the chat. Do baryons have an impact on the structure of the universe at larger scales beyond galactic scales?
Oh, yes, they do. So think about, for example, this picture here, okay? So the size of the galaxy is about here, okay? So this is about the size of the galaxy that we are visualizing here. But yet we have basically, like a really, really huge dynamo, like at the very center of this galaxy, which is the supermassive black hole, that is capable of ejecting, relativistic jets, which are streams of electrons, and those electrons collide and push gas out, far out, like much further out than the extent of the galaxy. So baryonic physics does in fact have an effect on larger scales. And this is why also this is something which is quite tricky to actually model. In fact, like my involvement in the Eagle Excel project is to get this right, okay? Because it's actually not an easy thing to do, but it does indeed have. So baryons do actually have an effect on larger scales. Not on the scales of the cosmic web. Okay, so this is much the cosmic web is much larger. For example, as you see here in this pie chart. So they don't affect the cosmic web. That's dominated by dark matter, but they do affect the galaxy classes, which are already much bigger than galaxies themselves.
Shresh, I think, is raising his hand.
Hello.
Ask away.
So I had a question. Sorry, I was not there for the earlier part, so I might have missed something. But there's a lot of computational challenge here, right? There's huge amounts of computations to get through, and you use massive supercomputer clusters to do these computations, and you just said about exaflop capacity. Mm-hmm. But in, like, let's say, for example, fluids and other stuff where there's also a lot of computational involvement, a way that some people solve that issue, or like even like traffic flow modeling and stuff like that, is instead of solving for like the Eulerian particle approach, you code in the rules and essentially try to cellular automaton or like let the system evolve from a set of simpler rules, which makes the computation less efficient, like more efficient and less intensive. Is there some way that this approach could work on a universe scale? Essentially, you divide it into small cells in 3D and code in the rules and then let them evolve?
Well, yes, that's actually a really, really good question. So in fluid dynamics, like most people use like Eulerian approaches. So basically, like your grid, and then you solve your PEs in the individual like grid elements.
Yeah, the finite elements. Yes.
Okay. So basically, like, we don't use Eulerian approaches. Okay, there are some people who use Eulerian approaches for for this type of simulations, but we use Lagrangian approaches. So basically, so the difference is that they are grid changes with time. Okay, so it actually follows the flow of the fluid. In our case, the actual gas. So we do have some implementations that are based on this kind of method. Okay, so it's not Swift, the code that we actually use for Eagle Excel, but there's a code called Arepo, which basically uses Voronoi tessellation to define some, you know, some little cells basically, and to solve the equations for each individual cell. So what we actually do is something different. It's a hybrid. Okay, so what we do is called multi-particle hydrodynamics. Okay, which is more efficient than some implementations, but with some drawbacks. Okay, so you lose on accuracy in some cases. So, but you know, this is the this is material for another talk. I would say.
Thank you. That was amazing. Thanks a lot.
Glad.
Seems like we have a couple more questions in the chat as well. In your simulations, is the dark matter you consider cold dark matter?
Yes. So there are also some people that do simulations with warm dark matter. So and what it basically, and the effect it has is that, for example, if you look at this picture, if you have warm dark matter, then a lot of these substructures will basically wiped out. Okay, so warm dark matter basically diffuses, you know, your material, like, you know, much more efficiently. Okay, so so like small structures have a much harder time to collapse, okay, than the bigger structures. So like you will still see, for example, like, you know, this big object here and those here, but all those smaller substructures will be wiped out. So your universe will be much smoother, if you want, if you had warm dark matter. Okay, so there are people like simulating warm dark matter, but this is almost certainly not the type of dark matter that we have in the actual universe, just based on the fact that if you had warm dark matter, like all of these like tiny galaxies or like dwarf galaxies will be wiped out.
We have another question. Are there better, if any, boundary conditions than periodic boundary conditions?
Well, you need to define what is better.
Yeah, I mean, I tried to type out the question, but I was, I think I made it too weird in the way that I wrote it. What I basically wanted to ask is like, I can see that maybe if you have larger galactic clusters, like in a simulation, if it goes off the edge, like, you know, if it's present at the edge and it comes out from the other side, so would it not like make an artificial sort of like mass accumulation on the other side? Like maybe there's a less mass on that side, like, you know, like if you have two sides on the road, like it feels like that wouldn't really happen in reality, like, you know, going from one side and popping in from the other. Like sometimes even a huge cluster can go from the other side and then come off from the other side. Like,
Yeah.
is it realistic?
Well, yes, no. Well, it could be realistic in the sense that it could be the case, because if you imagine you have like a field of view, okay, and like that one, for example. So if you see like a galaxy like moving out from your field of view, well, you know, according to some probability, then, you know, you can have pretty much the same probability of another galaxy from outside of the field of view, like on this side, moving in. Okay, maybe it's going to be not at the same height in this image, you know, but, you know, your matter balance, okay, your overall balance of matter, you know, that has to stay the same basically. Okay, so probabilistically it could happen, so it's not too far from reality, of course. You know, boundary conditions are convenient, but, you know, they're not the ultimate, the ultimate kind of boundary conditions. Okay, so there is, so I was having that conversation with a postdoc at JBCA that now is a UCL. So basically, like he was saying that, you know, what if you want to like simulate the boundary of the observable universe? Okay, so, and there are some tiny corrections that you need to take into account, but those corrections are small, and, you know, they wouldn't matter too much, you know, compared to all the other effects that we're taking into account. So boundary conditions are not something that we really are concerned by.